So let's continue talking about crystal structures for some commonly used metal. In this table you can see that aluminium, copper, gold, iron, lead, etc. Have a crystal structure of face-centered cubic. Yes, so in this table you can see, and also this table you can see interatomic distance of all element and atomic radius for body centered cubic element, for face centered cubic element, and for hexagonal close packed. For example, for magnesium, for titanium crystal has a crystal structure of hexagonal close packed and body centered cubic. So I hope you understand this. And now we talk about dislocations, imperfections, plastic flow, and strengthening mechanisms in metals. This chapter provides an outline of the crystalline structure of metals and explains, in terms of this crystalline structure, how metals deform both elastically and plastically. Depending upon the temperature, metals will contain a population of crystal defects, and it's these defects that make them capable of plastic deformation. By controlling the number, size and type of these defects, the strength and ductility of metals can be controlled to meet the requirements of many design situations. The presence of these crystal defects also influences in a major way the final failure and fracture of metals. You understand that metals are a group of materials of great technological importance in construction and in engineering generally. You know that metal also offer us tensile strength, which few of the traditional materials like natural stone or fired clay possess. Because of this remarkable combination of tensile strength and ductility, we can create all types of buildings and other structures that were not possible before the Industrial Revolution. Metals also offer fracture toughness, a resistance to brittle fracture not found in natural stone, clay, brick or concrete, and this makes them indispensable in the design and construction of many large buildings. Metal and steel in particular possess high value of stiffness. That is high value of elastic modulus. Young modulus is one of the major advantages of steel as a structural materials. Metal also possesses excellent electrical and thermal conductivities, particularly FCC metals, such as copper and aluminium. In the previous lecture, we have examined the nature of atomic bonding, and we have seen how metals as a class have very ordered crystal structures. Stress vs strain behavior of metals. I already said that metals, and particularly steel, are very important in construction and civil engineering. Indeed, the construction of most of the impressive buildings, bridges, and other structures created during the 20th century would not have been possible without steel. For this reason, it will be very advisable to examine the load-bearing behavior of steel. The stress vs strain graph obtained by testing a metal such as low carbon steel to destruction and shown in figure. We can immediately see that line consists of two regions. An initial linear portion followed by a non-linear portion. The last point on the curve, marked by a small cross, is the point of fracture. That is, this is the point at which the test piece can sustain no more strain, and it falls. In this case, we can see that failure has occurred at strain of 42.5%. This means that the test piece gauge length was 42.5% longer than it was at the start of the test. Furthermore, this 42.5% extension was permanent extension and was measured by putting the broken test piece ends together in an extensometer gauge and measuring the new length as at the point of fracture. What happened to the steel as it was strained from 0 to the point of fracture? What processes occurred inside the metal that resulted in the stress-strain graph being of the form that we observed? To answer these questions, we need to take a look at the structure of metal. That is, at how the atoms of which they are composed are arranged. So, it was a stress vs strain graph for a 0.1% carbon steel. And what about elastic behavior? The spacing between the atoms is the separation at which the force of attraction is exactly balanced by the force of repulsion. It's the principle of elastic behavior in metal. The result of these forces of attraction and repulsion is that resist any applied loading, and as a result we can model a metal crystal as a lattice where the atoms are attached to each other by spring, like you see at this figure. This spring model can help us understand the elasticity of metals. By elastic deformation, we mean temporary and recoverable deformation. We stretch a piece of rubber or a spring and it extends. When we release one end of the rubber of springs, it immediately springs back to the original length it had before we stretched it. We see exactly the same behavior in compression or torsion. A load deform followed by spring back when the load is released. This behavior is illustrated in the next figure. This shows both the tensile and compressive loading situation. If we apply a tensile load to our metal, we strengthen it and it resists our stretching. We can feel the resistance. What is happening and where does the resisting force come from? Remember, we are looking at elastic behavior. When we apply a tensile load to our metal, at the crystal level, it's like pulling the atoms apart. Our tensile load is resisted by the forces of attraction between the atoms. At the same time, our force acts with the forces of repulsion between the atoms. Therefore, the atoms move apart until the applied force is balanced once more by the forces of attraction. If we release our force, the attractive forces pull the atoms back to the original point of balance. And our temporary elastic extension goes back to zero. The same thing happens in reverse if we apply a compressive load. In this case, we work with the forces of attraction and against the force of repulsion. And so we get a temporary elastic compression. When we release our applied load, the forces of repulsion push the atoms back to their original spacing. And now we talk about fundamental property, about the elastic modulus or stiffness. When we apply any load to any structure, it will deflect elastically. even with weight of a couple of seagulls standing on a battleship gun barrel will cause it to deflect elastically. In this case, the deflection will be too small to measure with any extensometer or normal stray measurement device, but deflection will occur nevertheless. Finally, note that with elastic deformation, the atoms stay in the same relative positions to each other. So no atom shifts its position relative to its neighbors. The value of Young's modulus depends upon the strength of the bonds between the atoms in the crystal. This bond strength also plays an important part in determining how strong the metal. We also find that, as a general rule, elements having high strength and hardness also have high values of elastic modulus, Young modulus, and melting temperature. And the data in table illustrate that diamond, which has the strongest bonding, between its atoms, has the highest value of strength, stiffness and melting, and softening temperature. Lead, with the weakest bonding of the materials shown, has the lowest value in each case. In construction, we require materials with a high stiffness for the structural or load-bearing elements of our building. By high stiffness, we mean capable of load-bearing with relatively small elastic deformation. For example, the Empire State Building in New York weighed something over 300,000 tons. And this enormous weight has to be carried by the structural frame of the buildings at ground level. As we move up the building, the load that has to be carried by the structure at that level decreases, of course. However, 300,000 tons is a very high load, and it's important that the material of the frame is both strong in compression and also of high stiffness. In fact, the Empire State Building is about 165 millimeters shorter than it should be in the unloaded condition, purely because of its height weight. And the frame of the Empire State Building is made from steel, which is both strong in compression and also of high stiffness. To gain an idea of what is involved in elastic deformation, imagine a piece of material being loaded in tension. Looking at this figure, we can see that the load is carried by all the bonds in the cross-section of the material. The result, as we know, will be a slight increase in the length of the piece of materials. If we release the tension, the piece of material will immediately spring back to its original length. This is elastic behavior. Elastic strengths are temporary and are relaxed as soon as loading is removed. The same things will be observed if we apply a compressive load. Having examined elastic behavior, now let us look at plastic behavior. And what is the plastic behavior? This is something sometimes referred to as inelastic behavior, to distinguish it from elasticity. Plastic strains are permanent strain. There is no spring back. Since there is a permanent shape change when plastic deformation occurs, there must be some relative movement of the atoms in the crystals. Furthermore, this movement must be able to occur without fracturing of the crystal. And what mechanisms allows this to happen? The strength line reaches a peak and then in the case of steel it falls, and thereafter the line is non-linear. This nonlinear behavior is called plastic deformation. The elastic or straight line behavior is a fundamental property of the metal, and Young modulus is a constant for the particular metal. The plastic behavior is not fundamental, and the shape of the plastic flow curve can vary depending upon how fast we deform the metal or upon the state of stress in the metal or upon the temperature of the metal. The end of the plastic flow curve is the process of fracture, when the metal reaches the limit of its capacity to deform further and it falls. What mechanism is required to accomplish this? The answer lies in a type of crystal defect called dislocations, and we shall examine them next.